Next, we discuss the concept of continuity equation and relaxation time. And we say that from the principle of charge conservation, the time rate of decrease of charge within a given volume must be equal to the net, I should have highlighted this one, must be equal to the net outward flow of current. Talking about the time rate decrease of charge within a given volume must be equal to the net outward flow of current through the surface of the volume. That is the general principle of conservation. And this law of conservation simply says that if you introduce some charge to a volume, this is charge Q, at a rate of t, this will be equal to the current that will be flowing out of that volume of that material. Therefore, this principle says that there can be no accumulation of charge anywhere in the medium. So, and therefore we observe, we can state the principle of conservation of charge, like the current that is flowing out is equal to the rate of charges that are incoming. And therefore, this is described based by the current density. You can just express this flow of current by the current density over time, and therefore integrated over the surface, so that if you say that I is always expressed as J times the surface. So this is just the best way you can express that. Therefore, we have now to define this equation, we say that the Q in is the total charge enclosed by the surface. Therefore, from this equation, if we invoke the divergence equation, if you remember, if we had a surface integral on the one side, we say that this is equivalent to the divergence of the term J, or of your vector over the volume, integrated over the volume. And that is what we did. We said about the divergence theorem. So that is nothing new. We have already met it. And therefore, we just change this term to take this form. And we also know that there is something we know about the current flow, or the rate of change in charges over time, that we can say that charge Q is equivalent to volume charge density integrated over the volume. That is another principle that we have always known, that Q is equivalent to volume charge density of V integrated over the volume dV. Therefore, that is what we are now changing here. Therefore, this Q in, we are replacing it with the volume charge, the volume integral or volume charge density. And therefore, when we do that, we can just introduce the time derivative to the volume charge density, and therefore we end up with the equation as it appears in 542. And now, if we substitute equation 541, this one, and 542 into 540, what we end up having is something that is close to this, that we are replacing this term, and we are replacing it now with, sorry, we are replacing it with that term, and therefore on our left we have divergence of J integrated over volume dV, and therefore on the right we take this term and we bring it on the right, which is on the right of this equation, what we had on the right, and therefore we end up with what we have already found here. And if you now notice that both of them are volume integrals, it becomes straightforward to pick out the terms that are under the integration. So we can pick this term and leave out the integrals. Therefore, we are going to be left with divergence of J is equals to negative partial time derivative of rho V. And therefore, this equation 543 becomes a very important equation. And this is the equation that we define as the continuity equation that relates the current density of with the rate change of increase, or rate of change of the volume charge density in a volume. And we are now saying that it must be kept in mind that the continuity equation is derived from the principle of conservation of charge, and this states that there can be no accumulation of charge at any point. And that is a point that I mentioned very earlier in when I was introducing this concept. Therefore, for steady currents, we know that the rate of increase of volume charge density over time can only be equal to zero, because current is coming. It's talking about steady current. So current is coming, and then it is leaving there. Therefore, the rate of change of volume charge density rho v inside this volume can only be zero. And therefore, we say that it observes this zero, and therefore the divergence from this equation 543, the divergence of J can only be equal to zero then. Therefore, showing that the total charge leaving a volume is the same as the total charge entering the volume. So charge is increased coming here, and charge is coming out there at that point. And therefore, this is how or where or how the Kirchhoff's law is defined. And therefore, having discussed the continuity equation and the properties of sigma and epsilon of the materials, it is appropriate to consider the effect of introducing a charge as a material point of a given material. And we make use of this equation in conjunction with Ohm's law. And we say that we can be able to define Ohm's law in this format. And we did this, and therefore this is not very strange, because this equation characterizes the medium, this characterizes the voltage, and this characterizes the current. So we normally say that the basic form of Ohm's law is equals to voltage over resistance. And therefore, because we are able to characterize the resistance in terms of conductivity when we are defining the resistivity, and we have said the voltage is expressed as ED is equals to V, and therefore this simply purely B is a function of E, and therefore J is also a function of current. And therefore this equation holds. This is another definition of the Ohm's law. So we are using three items: equation 543, equation 5444, and the Gauss rule. The Gauss rule we met earlier. It states that the divergence of E is always equivalent to rho v over epsilon. And the basic definition of Gauss rule, it was not in this form. It was in the form divergence of D is equals to rho v. That is said that if you have a medium and the flux inside passing through this medium is only equivalent to the charge enclosed herein. And therefore this is how we define the Gauss rule. So we are simply saying, since we know D can always be expressed as epsilon E, therefore we can divide by epsilon here and epsilon here, and here we are left with E, and therefore we have divergence of E is equal to rho V over epsilon. Therefore we have equation 545, 544, 544 here and 543, and from those three equations we can just come up with another interesting substitution. And what we are going to have is that from equation 545, if you work with 544, where we said that the divergence of the J is equal to sigma E. Okay, I have just written 543 here, and we have said that divergence of J is equals to negative time derivative of rho V. And since we know J to be equals to sigma, why is that? J is equals to sigma E. So if you replace this term with sigma E, we end up with this. And on the right, we have rho V over epsilon. This is the equation that we had in on the right. Remember our starting equation was equation 543. I've just deleted it here for the convenience. So we have already manipulated the left hand side and we have obtained this term. And on the right hand side, where we had negative time derivative of rho v, which is already stated here. But before we go beyond, and that is what we still have here. So before we want to find out how are we getting to this term. So before we go further, we just know that this term is equivalent from the equation that we have just stated, that from equation 545, we have stated that so from again from this equation we are simply saying that we know this to be true, and since we want our equation to be this form, if you introduce sigma e here and sigma e there, sorry, sigma e on both sides, you have this term being equivalent to j. And therefore, on our left we have sigma j, and on our right we have sigma j. So we have sigma rho v epsilon, and this is how we get that term here. So now, having gone that, we can now get rid of this term because it's on its own, and therefore we are left dealing with this expression, which is the one we tend to work with. Therefore, what we end up with is that if you bring the right terms together, you bring this term on this side, you have log v dt plus this one, you have log over epsilon log v is equal to 0. And what we observe about this equation is that it is a homogeneous linear ordinary differential equation, which we can solve by separating the variables. That is, from this one, you divide by log v everywhere, log v, and multiply both sides by dt, you end up with dt. On the right, we have 0, this goes, so we are left with dd law over law is equal, the first one before we get here is that d law v over law v plus sigma over epsilon dt is equals to 0. Therefore, of course, when you bring one on the other side, it becomes negative. And therefore, to solve this equation, you'd simply integrate both sides because of both of them has a derivative or partial derivative. And for that reason, what you end up getting is that the integral of d log v over log v is equivalent to ln of rho v. And this, when integrated over time, it becomes t with this as a constant, then plus constant of integration, log v, that is on this side. We are saying that the ln of log v is a constant of integration that we have chosen to be that form. Therefore, we can now just use our knowledge of ln such that if you raise both sides with ln, you know, if you have ln of x is equals to constant k plus ln of something, you can bring this on this side, you can, and you have ln of x y, ln of x minus ln of y is equals to constant. This is equivalent to saying ln of x over y is equals to constant. Therefore, when you say e, you raise this thing, ln of x of y is equals to exponent of k. Therefore, ln cancels out this one, and you are left with x of y is equals to e of k. Therefore, if we choose our k to be this term, and therefore this means that, and our x was this, our x was rho v, and our y was log v naught, and therefore we end up with rho v is equals to log v naught exponent of minus t over TR. So if, of course, we have chosen TR to be equivalent to reciprocal of this, which is epsilon over sigma, and we revert to TR as sorry, and TR becomes, or we call it the time constant, and TR we just chosen to be equivalent to that term. So that is a very important realization, because it defines for us what is called relaxation time. And before we actually talk about that, we say that log V is the initial charge density. So we talked about when you have a volume here and you introduce some charge inside the volume, and there's something that this equation tells us. This equation tells us that this charge will attempt to leave the volume and come to the surface, such that there will be no accumulation of charge inside the volume. And therefore, we are saying that, that being said, the law V is the initial charge density at time t is equal to 0. The equation shows that the introduction of charge as a material point of the material results in a decay of volume charge density law V. So if this material had a law V and then introduce some charge, then law V will decay. Associated with the decay is a charge movement from the interior towards the exterior, such that the time constant is the time that it takes for the charge introduced at the center to move to the surface. It is now saying that the relaxation time is the time it takes a charge placed in the interior of material to drop to exponent of -1, which is a reciprocal of the natural number, which normally becomes that it is equivalent to that 6.8%. And I believe you guys know the natural number. Natural number is always is a constant, just the way we have pi is equal to 3.142, etc. A natural number E is considered to be a constant that has the value 14883, and this is always constant. So we are saying that if you take E per 1 is equivalent to 1 over 2.7183 times 100. So we are looking at the percentage of this one, and doing that very quickly, I get that this becomes 36.8%. So that is how we get this figure. So lastly, as we say that we want, what we are trying to derive is this term, yeah, the relaxation time, and we have derived it. And the relaxation time is short for good conductors and long for good dielectrics, such that in conductors we see that the decay of a charge introduced in a good conductor becomes almost like decays immediately with a very short span, which we shall see here, that the decay for a good conductor is a very, very short. And that is how we say that there's a very rapid decay of charge placed inside a conductor or copper. And this implies that for good conductors, the relaxation time is so short that most of the charge will vanish from any interior point and appear at the surface of the conductor almost instantaneously. On the other hand, a very good dielectric, such as a fused quartz, may have has a relatively low conductivity and a high permittivity or relative permittivity, and therefore when you calculate the time constant, you end up with about 51 days, which is a very large relaxation time. And thus, for good dielectrics, one may consider the introduced charge to remain wherever placed for some time, up to some few days.